أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. Now, classically, I should start by saying Muslims begin their work in the name of God, the most gracious, the most merciful, as taught to us by the Prophet Muhammad sallallahu alaihi wasallam. May the peace and blessings of God be upon him, his family, and noble companions in abundance. Now, I'll leave it there as I don't want to get into a religious discussion, as I'm not directly aware of a philosophical or linguistic connection between the Islamic faith and governing principles within fluid dynamics, or at least not according to my understanding. We'll leave it there and we'll go through a short recap of what I've discussed in some of my previous uploads. Now we're taking a slightly different angle, especially in terms of modeling surface reflections onto the real plane. Now we discuss the environment and how that can be mapped onto the R plane. Now we also discussed how the blinds, which are ahead of me, can be mapped onto the R plane using reflections, and how we can use vector calculus, vector algebra, and other general topics of mathematics to describe objects within the environment. But what I didn't get into was fluid dynamics and the solutions governing fluid dynamics. Now, in the videos that I've shared alongside this one, so you can see towards the left of the screen, you can see the models above the sloping boundary. We can use this to describe turbulent flow over the wing of an aircraft. Now, how it's made is essentially from interactions with fluids and using light, which, looking at the model, is being emitted from the bottom right corner of the irregular shape. Now, in terms of the mathematics, again, towards the bottom left corner, you can see, or I should say, the bottom right corner, you can see the XY plane, as well as the transformation on from R3 onto R2. Now, in the simulation which is being run through, it's on a loop, so it's being repeated. So as it goes towards the end, it will then be repeated in line with the length of this video. And so you can see how one can simulate turbulent flow, or the turbulence experienced by aircraft and jet engines during flight. As you know, we're unable to create a computational algorithm which can accurately model this simulation, which is, in terms of its one-to-one principles, or an accurate projection from R3 onto R2. And this again is using airflow, momentum, viscosity, light, and other forces, as we've discussed, gravity as well. Now, in the video that I've shared alongside this video, I've run through the simulated clips and the models which can be used in aerospace systems, which enhance our understanding, using multi-phase fluids for simulating turbulent flow over jet engines and aerofoils. Now, I won't be going into the mathematics, so I won't be writing anything onto the board, Although, so why I have this pen, I actually don't need it. So I'm just going to place that over here. But we'll go into essentially now the mathematics is all explained towards the bottom left corner, or the bottom right corner, I should say, representing a transformation from R3 onto R2. We have the sloping boundary. Now, previously I mentioned that the specific problems with accurately modeling turbulent flow experienced by aircrafts and the limits faced by computational algorithms in solving this problem. And I also mentioned in previous videos that we can use our basic understanding of airflow, momentum, as well as light to essentially model the behavior of turbulence over time. And so you will see various combinations that I've employed to model this behavior, in which case you will see a sloping boundary and a mapping from R3 onto R2. I must be very explicit in terms of the language that is being used here, as we're modeling the behavior of turbulence rather than the experience of turbulence faced by an aircraft in flight. But we can use our basic understanding of airflow, from momentum, viscosity, and light from energy. And so in the previous video, we also spoke about energy emissions and the changing radius over time, which again is explained, which I've labeled in the video that I've shared alongside this one. In terms of modeling turbulence, human beings can also breathe out turbulence. And so it's fascinating in many ways. But in terms of actually creating computer code or using a modern programming language, what we do know is that this can't be done. But in terms of isolating a single occurrence of a turbulent event, one can do this using algebraic structures, as we discussed in the last video when we went into surface reflections. We spoke about vector spaces, vector algebra, and calculus, and how we can use those techniques to design a program such as this. And finally, as well, in the clips that you can see with the jet engine, you can see this overlapping with our discussions on energy emissions and the changing radius, which changes according to the angle theta and time t. This again is described in complete terms following the projection onto R2. And so we have the equations which can describe that behavioral change. And last but not least, we should also mention that the jet streams which are being emitted from the aircraft are not only turbulent but also are contributing to the emissions of greenhouse gases within the atmosphere. So in terms of our complete descriptions of the video content shared alongside this one, we should have now covered We've covered the various combinations of the same event, and we've also covered the mathematical descriptions of that transformation from R3 onto R2 in the XY plane, as well as simulating the behavioral characteristics of turbulence over an aircraft within flight, though not the exact description of what of the turbulence experienced by that aircraft during flight. As we know, we have no programming solution or algorithm that can accurately model the effect an aircraft experiences when encountered with turbulence. Yeah, this one was fairly short, so we'll leave it there and leave the discussion to another time. And yeah, I hope everyone had a great New Year's.
محمد خير من يمشي على